Welcome to another module in this massive open online course. So we have looked at the principles of decoding a convolutional code, and now let us look at how to actually apply these principles in the decoding of the received word in a convolutional code. And this decoder, which finds the maximum likelihood estimate of the transmitted code word, is known as the Viterbi decoder, which is a very important and celebrated algorithm in communication, which has made you can say modern communication or modern communication possible at a very low error rate. Okay, so what we are going to look at is the Viterbi decoder for a convolutional code, which was proposed by Andrew Viterbi. And we are going to illustrate this through an example. Okay, so we are going to consider an example, and of course goes without saying this is a trellis based decoder. That is why we have been building up and emphasizing the importance of the trellis. Okay, this is a trellis based decoder. Let us look at the received sequence R bar equals 1 1 1 1 1 0 0 1 1 0 1 0 1 1. Okay, 0 0 1 1 0 1 0 1 1. Now corresponding to this, let me begin by drawing the trellis diagram. Okay, so I will begin by drawing the trellis diagram corresponding to this. So what I have over here is basically the first stage of the trellis. So let me start by drawing the first stage of the trellis diagram. Okay, so this is your states 0 0 1 0 0 1 and 1 1, and we know at the next time instant we have a similar repetition of the states. So at the next time instant we have again 0 0 1 0 0 1 1 1, and now we show the transitions. Remember, there are each state splits into two arrows. So there is a top arrow, there is a bottom arrow, top arrow, there is a bottom arrow, top arrow, there is a bottom arrow, top, and this structure is repeated. The top arrow denotes 0, output 0 0, input 1, output 1 1. Okay, state 1 0 0, outputs 0 1, the bottom arrow denotes input 1, state 1 0 0 1, input 0, outputs 1 1, input 1, output 0 0, and state 1 1, input 0 denotes output 1 0, input 1 denotes output 0 1. Okay, corresponding to the bottom arrow. Okay, and now we see that the received word corresponding to this is 1 1. So I am going to write it here at the top of this. Okay, on the top of this trellis I am going to write the received code word. So this is corresponding to the states at j equal to 0, states at j equal to 1, and the received code word is 1 1. Now you see at time j equal to 0, we assume that we are starting from the state 0 0. So I am going to set the d min. On each state I am going to write the d min. So d min to 0 0, the state 0 0 is 0. For all the other states I am going to set the d min as infinity. So at j equal to 0, so this is an important point, at j equal to 0, d min of the state 0 0 equals 0 and d min of any other state, or say for instance let me write it explicitly, d min of 0 1 equals d min of 1 0 equals d min of 1 1 equals infinity, just to show that these states we do not begin with any of, we begin at the state 0 0. So, there is the distance of, start with d min of the state 0 0 equal to 0. Now, if you look at this, now let us look at the branch between 0 and 0 to 0 0, state 0 0 to state 0 0, that corresponds to the output 0 0. So, the Hamming distance between the received code word, remember the total metric is the sum of the branch matrix. The branch metric is determined by two things: one, the received word corresponding to that time instant, which is 1 1, and 2, the output corresponding to that branch. The output corresponding to this branch is 0 0. So, the Hamming distance between 0 0 and 1 1 is 2. So, the branch metric corresponding to this branch is 2. Similarly, branch metric corresponding to this branch, which is output 1 1, received word is 1 1. So, the Hamming distance is 0. Similarly, branch metric corresponding to, if you look at 1 0, the top branch is 0 1, output 0 1, received word is 1 1. So, Hamming distance is 1. Similarly, the bottom branch Hamming distance is 1. Top branch 0 1, output 1 1. So, Hamming distance is 0. Bottom branch output 0 0. So, Hamming distance is 2, 1 1, top branch output is 1 0. So, Hamming distance from 1 1 is 1. Bottom branch, the output code word output, the coded outputs are 0, the coded output sim bits are 0, 1. Hamming distance between 0 1 1 1 is 1. Okay. Now, remember we use principle number 2. Now, look at this. At stage 0 0 at time instant j equal to 1, I can either arrive from 0 0 or I can arrive from 0 1. So, if you write this separately, look at this. I have stage 0 0 at j equal to 1. Now, I can either arrive from 0 0, the corresponding minimum distance to 0 0 is 0, and the branch metric, remember, is 2, which is the distance between 0 0 to 0, or I can also arrive from the state 0 1. If you look at it, I can arrive from the state 0 1 also to 0 0. The corresponding branch metric, if you look at this, the corresponding branch metric is 0, alright. The corresponding branch metric is the top branch, which is 0, but the distance, minimum distance to 0 1 is infinity. Remember, we initialized it as infinity. Therefore, now at j equal to 1, d min to 0 0 equals minimum of, well, distance to 0 0, that is 0, plus distance from 0 0 to 0 2, and infinity plus 0, that is distance to 0 1 and distance between 0 1 and 0. So, this is distance to 0 0, this is distance from 0 0 to 0 0, this is d min to 0 1, and this is distance from 0 1 to 0 0. And now you can see this is equal to minimum of 2 comma infinity, which is naturally equal to 2. So, the minimum distance is 2, and the minimum distance branch is Remember, at each state I need to store only the minimum distance, remember that is our principle number 1, minimum distance, path, and what is the minimum distance, right? So at each state store only the minimum distance path. At each state we store only the minimum distance path. So to 0 0 at time instant j equal to 1, the minimum distance is 2 and the minimum distance path is from 0 0, take the top branch with output 0 0 and branch metric 2. Now similarly, if you look at the state 1 0, now 1 0 I can come to 1 0 from 0 0, or I can come again, I can end up in 1 0 from 0 1 at time instant j equal to 0. So the minimum distance to 1 0 again is minimum of the distance to 0 0, that is 0 plus the branch metric 0, or infinity, that is the distance minimum to 0 1, minimum distance to 0 1 plus the branch metric between 0 1 and 10, that is 2. So the minimum distance, now you can see d min to 0 1 or to 1 0 at time j equal to, this is equal to, I can come from 0 0, d min to 0 0 is 0 plus 0 the branch metric, or I can come from 0 1, the d min to 0 1 is infinity plus the corresponding branch metric between 0 1 and 1 0 is 2, which is equal to minimum of 0 comma infinity, which is clearly equal to 0, and therefore the d min to 1 0 is 0 and the minimum distance path is this. Now here if you look at 0 1, now if you look at 0 1, 0 1 I can come either from 1 0 which has d min infinity, so the minimum distance to 0 1 is infinity plus the branch metric 1, or I can come from 1 1 again which has a d min infinity, so the distance is again infinity plus 1, so the minimum distance is minimum of infinity plus 1 comma infinity plus 1, which is any case is infinity, so it does not matter, I can take whichever path. Again similarly the minimum distance to 1 1 is also, you can see, infinity, because I can either come from 1 0 or 1 1 and both of them have the minimum distance of infinity. And you can see that at every stage, at each time instant, for every state I am noting two things. One is the minimum distance to that and the branch corresponding to that minimum distance, because we are going to need that later, because when we find the minimum distance path, that is the path through this trellis which corresponds to the minimum distance metric, minimum Hamming distance with respect to the received word, I am going to need these minimum distances and the corresponding path. Okay, and now we can repeat this at every subsequent time instant. For instance, again I draw the next stage of the trellis. This corresponds to the received word 1 1 again, at the time instant j equal to 1, received word is 1 1. Once again the minimum, the branch matrix will be the same, 2 0 1 1 0 2 1 1. Minimum distance to 0 is, I can come at j equal to 2, I can come to 0 0 from 0 0, so minimum distance is 2 from 0 0 plus the branch metric 2, or I can come from 0 1, minimum distance is infinity plus 0 from 0 1, so the net minimum distance to 0 0 is minimum of 2 plus 2 or infinity plus 0, which is basically minimum of 4 comma infinity. So the minimum distance is 4. For 1 0 and the minimum distance path, do not forget to mark the minimum distance path, that is the branch between 0 0 and 0 0. Now 1 0 I can come from 0 0, the distance is 2 plus 0, or I can come from 0 1, distance plus is infinity plus 2. So needless to say the minimum distance is 2 plus 0 from 0 0, so that is 2, and this is the minimum distance branch. 0 1 I can come from 1 0, right, or I can come from 1 1. From 1 1, 1 1 has a minimum distance of infinity, so it's infinity plus 1. From 1 0 it is 0 plus 1, so needless to say the minimum is 0 plus 1, that is a minimum distance of 1 to 0 1. To 1 1 I can come either from 1 0, the minimum distance is 0 plus 1, the branch metric, or it is infinity plus 1 from 1 1. Needless to say the minimum is 0 plus 1, that is 1, and that comes from 1 0. This is at j equal to 2. Similarly, I can do j equal to 3, which is 0 0, 1 0, 0 1, 1 1, I have all the branches. You can keep doing this. J equal to 3. The received code word corresponding to this is 1 0. The branch matrix will change. The branch metric, the top branch 0 0 to 0 0, that has an output. The output is 0 0. So Hamming distance between 0 0 and 1 0, that is going to be 1. Hamming distance, bottom branch output is 1 1. Hamming distance 1 1 and 1 0 is 1. So the Hamming distances are 1 1. Hamming distance now 1 0 corresponding to 1 0. Top branch will have Hamming distance 2 corresponding to 0 1. Bottom branch is 1 0. So Hamming distance is 0. 0 1, 1 1 corresponding to, so Hamming distances will be 1 and 1. Again from 1 1 there are two branches, 1 0, that top branch is output 1 0, that will have Hamming distance 0. Bottom branch is output 0 1, so that will have a Hamming distance of 2. And once again the minimum distance to 0 0 is either minimum of 4 plus 1 from 0 between 0 0 to 0 0, 4 plus 1, or it will be 1 plus 1 from 0 1. Distance minimum distance to 0 1 is 1, branch metric is 1, and needless to say minimum is minimum of 4 plus 1 and 1 plus 1, so the minimum is 1 plus 1, that is 2, and this comes from 0 1. Okay, this comes from, and this is your minimum distance path. To 1 0 the minimum is either 1 plus 1 or 4 plus 1, once again it is 2. Okay, so once again it is 2, and it comes from 0 1. Distance, minimum distance to 0 1 is either 2 plus 2 from 1 0 or 1 plus 0 from 1 1. So minimum is 1 plus 0, that is 1, and that comes from 1 1. And finally between to 1 1, either you can come from 1 0, that is 2 plus 0, or from 1 1, that is 1 plus 2. The minimum is 2 plus 0 from 1 0, so that corresponds to minimum distance of 2. Okay, so that is corresponding to j equal to, that corresponds to j equal to 3. So we have corresponding to j equal to 3. So I am going to quickly draw the rest of the stages of the trellis. Just save some space because I am going to need it later. 2 more stages. That is what we are going to need. 1 0 0 1, and you can see what I am doing is I am simply repeating all the states at each stage. So now I am going to draw the branches. This is very simple because all you need to do is you have to repeat the trellis. You have to repeat the stages. At every time instant. It's a repetitive structure which makes it very convenient and advantageous. I am just going to complete this example for the purpose of illustrating it. Okay, and now you can see this corresponds to J equal to 5, J equal to 6, J equal to 7. I am going to quickly keep writing down the received word 1 0 corresponding to J equal to 3, that will be 0 1. The branch matrix will once again be for the two branches from 0 0 1 1. Branch matrix corresponding to 1 0 because it will be 0 1, top one is 0, output 0 1, so this has a branch matrix 0, bottom one will have a branch matrix 2, 0 1 it's 1 1 and 0 0, so again branch matrix will be 1 1, and here again 1 1 1 0, so branch matrix is 2, and lower branch will have 0. The minimum is 2 plus 1. At j equal to 4 to 0 0, you can either come from 0 0, so minimum is 2 plus 1, or 1 plus 1 from 0 1. So needless to say, the minimum will be, well, 2, and the minimum branch will be this. To 1 0 to 1 0, the minimum will be either from 0 0, so it will be minimum of 2 plus 1, or a minimum of 1 plus 1 from 0 1. So naturally the minimum is 1 plus 1. So this will be minimum of 2, and to 0 1 I can either come from 1 0, so 2 plus 0, that is 2, or from 1 1 2 plus 2, that is 4. So the minimum is naturally 2 plus 0, that is 2, and the minimum branch is between 1 0 and 0 1. And to 1 1 I can either come from 1 1, that is 2 plus 0 2, or from 1 0, that is 2 plus 2 4. So needless to say, the minimum distance branch corresponds to this. Now look at state j equal to 5. The minimum distance between to 0 0 will be either, so the branch matrix, now the corresponding received word is again, so after 0 0 this is 1 0. The minimum distance, the branch matrix will be again 1 1 1 1 and 0 1, so this will be, top branch will be 2, bottom branch will be 2, bottom branch will be 0. Between 0 1, top branch will be 1, bottom branch will be 1, and from 1 1 the top branch will be 0, bottom branch will be 2, because bottom branch corresponds to output 0 1, having distance between 0 1 and 1 0 is 2. So again, if you look at to 0 0, I can come via 0 0, that is minimum distance will be 2 plus 1, that is 3, or from 0 1 minimum distance will again be 2 plus 1 3. Now here what we see is we have a tie. When we have a tie, then obviously the minimum distance can correspond to anyone. So we can choose any particular branch, it does not really matter. Okay. So in this particular case, I can come to 0 0, from 0 0 the distance, minimum distance will be 2 plus 1, or I can come from 0 1, minimum distance will again be 2 plus 1. So I can choose any particular branch. Okay. So in this case, I will choose the top branch. Okay. So this will be 3. To 1 0, I can come again from 0 0, 2 plus 1, that is 3, or I can come from 0 1, which is again 2 plus 1 3. So I can pick this, which is 3. To 0 1, I can come from 2 plus 2, 2 plus from 1 1, that is 2 plus 0, or 2 plus 0 2, or I can come from 1 0, that will be 2 plus 2 4. So needless to say, it will be 2 plus 0, that is 2. To 1 1, I can come from 1 1, that is 2 plus 2 4, or I can come from 1 0, that is 2 plus 0 2. So needless to say, it will be 2. Needless to say, it will be 2. Again proceeding to j equal to 6, again j equal to 6, the received word is 1 0. J equal to 6, the received word is 1 0. So 0 1, let me just check, 1 0, and the final one is 1 1. Let me just write that as well, 1 0 1 1. And again, if you look at the branch matrix, they will be the same. Okay, whenever the code word, received word is the same, the branch matrix are going to be the same, right, because the code word outputs for each branch are fixed. Okay. So this is 1 1 1 1. This is again going to be, let me just write it with a different color. This is 1 1 2 0, again 1 1, and 1 1 1 0. So 0 2. Minimum distance to 0 0 is either 3 plus 1 4 or 2 plus 1 3. So needless to say, it is 2 plus 1 3. 2 plus 1 3, and minimum distance to 1 0 is either 2 plus 1 3 or 3 plus 1 4, and it is again 2 plus 1 3 from 0 1. To 0 1, it is either 3 plus 2 5 from 1 0, or 2 plus 0, that is 2 from 1 1. So needless to say, it is 2. And for 1 1, it is either 3 plus 0, that is 3, or 2 plus 2, that is 4. So needless to say, that is 3. So we have 3 3 2 3, and in the final stage, the distances, the branch matrix are going to be, well, the branch matrix, the top branch 0 0 to 0 0, that is 0 0. So the Hamming distance is 2 0, again 1 1, 2 0 1 1, and this one from 1 0 1, the branches are 1 1, which will have a Hamming distance 0, or 0 0, which will have a Hamming distance of 2, and the bottom branches will have a Hamming distance of 1 each. Okay. And now once again, you can find the minimum to distance to 0 0 is 3 plus 2 5, or 2 plus 0 2. So that will naturally be 2 plus 0, that is 2. Minimum distance to 1 0 is 3 plus 0, that is 3, or 2 plus 2, that is 4. So naturally it will be 3 plus 0, that is 3. Minimum distance to 0 1 will be 3 plus 1 4, or 3 plus 1 4. I can choose either one. So that will be 3 plus 1 4, and finally minimum distance to 0 1, I can come from 1 0. The minimum distance corresponding to that is d min to 1 0 3 plus the branch metric 1 4, or 3 plus 1 4, corresponding to coming from 1. I can choose either one. So basically, if I choose this branch, this will be 4. Okay. And so now what I have done is, basically after this procedure, it might, I understand it might be a little bit confusing, but I urge you to go over this again to understand it. Basically we have done nothing but use the two principles which we have clearly explained or elucidated in the previous module. That is, basically at every state, at every time instant, I only need to store the minimum distance and the path the minimum distance path that leads to that state at that time instant. And 2, whenever you are trying to find the minimum distance to a state at a time instant from states at the previous time instant, remember there are 2 states at the previous time instant which will lead to the state at the current time instant. So I have to find the minimum distance from either state. Will be, for instance, let us say S0 and S1 are the minimum states that lead to S2. So it will be minimum of distance to S0 plus branch metric between S0 and S2, or and the minimum of S distance d min to S1 plus the branch metric between S1 and S2. That is the principle that we have seen. Okay. For instance, let me just go back and look at what we have done in that. That is, the minimum distance to Sk from states I and j will be minimum of di, d min to state I plus the distance between state I and state k, comma dj minimum distance to state j plus djk, that is a minimum distance, that is a branch metric between state j and state k. Okay. So that is basically what it is. And now you see at the final state we choose the one that is the minimum distance. The one that is the minimum distance is basically the 0 0, and therefore now we will trace back the path. At this point we will trace back the minimum distance path, because we have stored the minimum distance branch for every state. Trace back and to trace back the minimum distance path, now all I have to do is trace back these, basically the minimum distance branches. So basically that gives me, if I am going to put it in a rectangle, so the minimum distance comes from 0 1 to 0 1, the minimum distance comes from 1 0 1 1 to 1 1, the minimum distance is this, to 1 0 the minimum distance is this, and to 0 1 the minimum distance is this, through 1 1 and to 1 1 the minimum distance is, so 1 0 and to 1 0 the, and to 1 0, wait, there might be a slight, apologize for this, and to 1 1 the minimum distance is to 1 0, and to 1 0 the minimum distance is from 0 0. So the state sequence will be now back trace, and now you can draw the state sequence will be, you can see 0 0 to 1 0 to 1 1 to 0 1 to 1 0 to 1 1 to 0 1 to 0 0. So the minimum distance path is indicated by the rectangles. Okay, we have back trace. So let me just mention it. These rectangles denote we have back traced. Basically what we have done is, at this point we have back traced to find the minimum distance path, and now the minimum distance, the rectangles denote the minimum distance path, and correspondingly reading that minimum distance, that states along the minimum distance path, I can find the state sequence. So the state sequence corresponding to minimum distance path, or basically the maximum likelihood state sequence, so the state sequence for your minimum distance path, now you can see this is basically the state sequence is 0 0 1 0 1 1 0 1 1 0 1 1 0 1 and 0 0. This is the state sequence. Remember, this is not the output code word. Now, the decoded code word will be the outputs corresponding to this state sequence. Okay. So, the decoded code word will be remember this is the maximum likelihood decoded code word, that will be, well, the decoded code word will be 1 1. You can just look at it. For instance, corresponding to this branch, it will be, this is the bottom branch, so 1 1. Next is the bottom branch of 1 0, so that will be 1 0. Next is the top branch of 1 1, that is basically 1 0, and so on. So basically you will get the decoded word 1 0 1 1 1 0 1 0 0 0 1 0 1 0 1 1. So that will be 1 1 1 0 1 0 0 0 1 0 1 0. And now if you look at this with respect to the, and remember this is the maximum likelihood decoded code word, this is the maximum likelihood, it is not guaranteed obviously. Now, one thing you have to understand, it does not automatically mean that this is the actual code word that has been transmitted. You have to realize that this, there can still be an error. This only denotes the maximum likelihood estimate, that is, what is the code word corresponding to the received word that has the maximum probability of having been transmitted. That is, which one is in which one has the maximum likelihood of having been transmitted corresponding to the received word. That is all this says. And now if you look at the received code word, the received word is, well, let me just write this again. One zero 0 1 1 0 1 0 1 0. Okay, and what you can see is basically you have the Hamming distance between this and this is basically you have 2 errors between the received word and your maximum likelihood. There are 2 places of mismatch, and that is what in fact we had seen when we have completed the Viterbi algorithm, the final. So, this 2 places of mismatch, 2 mismatched bits implies DH between C bar decoded code word and R bar equal to, and in fact the Viterbi algorithm guarantees that this is the D min, and that is what we have seen. Remember, from the final state, this is your D min, that is the minimum Hamming distance, that is the code word this corresponds to the path with the with the minimum path metric, which also is the minimum Hamming distance between the code word and the decoded code word and the received word. In fact, that is what we are trying to do. By adding these different branch metrics, we are trying to find the path which corresponds to the minimum distance between the received word and the possible code word. Alright, the code word which has the minimum distance corresponding to the between the minimum Hamming distance with respect to the received word. Okay, and therefore this is the decoded code word. We have used the Viterbi algorithm to decode this, which is very important to remember. As I emphasized, most modern communication system, digital communication systems employ one for Viterbi algorithm in one form or the other, that is Viterbi algorithm or different versions of it or one form of the other. In fact, this was one of the earliest possible codes that were employed in wireless communication systems and which have made reliable wireless communication possible even over noisy channels. That is, when the channels are very noisy, which lead to error prone bits at the receiver, reliable decoding, correct, reliable transmission over such channels is possible through the use. Remember, codes or convolutional codes basically are channel codes which are used to recover, that is basically both detect and correct errors that are occurring over noisy channels. And in fact, the Viterbi decoder is what made this low complexity decoding of convolutional codes possible, which in turn made reliable transmission possible over wireless channels. Okay. So with that, I think I would like to once again, and of course the decoded information bit sequence, you can also see from the path that the information bit sequence, remember, the information bit sequence, again from the path you will have 1 1 0 1 1 0 0. This is a maximum likelihood ML. So these are the ML decoded information. This 1 1 0 1 1 0 0. You can verify that. Okay, this is the decoded information bit sequence. Okay. So with that, what I would like to do is I would like to stop this module here. And as I have already told you, with this module we have illustrated the concept, the working of the procedure of the Viterbi decoder through an explicit example by carrying it out, illustrating it using a trellis and carrying it out through several stages. The procedure is slightly complex and can also be confusing at times, so I urge you to again go over this module if need be, so as to clear any doubts, and also try working through this example yourself to understand it to the best possible extent. All right. So I hope I've been able to explain this intricacies of the Viterbi decoder through this example. We'll stop this module here and look at other aspects in the subsequent modules. Thank you very much.